So thank you, Donna. So I already apologize to Jonah. There will be no SCPs being talked about today. So I'm going to talk about stellar winds and high energy radiation. I know we are in cool stars, but still my talk is a bit more motivated towards why we should care about these phenomena in terms of exoplanets. So let me first begin by talking about stellar winds and why are they important. So when we talk about stellar winds from an exoplanet perspective, we're interested in understanding how winds impact atmospheric loss. And in this particular case, we're interested in atmospheric losses due to non-thermal processes. So what I mean by non-thermal processes are phenomena such as sputtering, where you can have an energized ion from the stellar wind that can knock atmospheric atoms and molecules, which happens in Mars, for example. We could also have charge exchange processes where a fast ion can collide with a neutral in the atmosphere. And during this collision, the solar wind ion captures an electron and becomes a fast neutral, and that can get lost to space. And it's what we are left off with is slowly moving ionized particles in the atmosphere. Now, if we are a planet like Earth, where we have a magnetic field, then these magnetic fields do trap quite a lot of these ions, but magnetic fields also have open field lines, and particles can still get lost through these open field lines. So these kind of atmospheric loss processes are commonly referred to as non-thermal processes, and the stellar wind is responsible for driving these kind of phenomena. So this brings a question, when we look at exoplanet, the current exoplanet population, such as the rocky exoplanets around M-dwarfs, the question is, what kind of stellar wind properties do these stars have, and how can we constrain these stellar wind properties? So one way of actually detecting winds around cool stars would be charge exchange processes, and this is charge exchange between the proton that comes in the solar wind or the stellar wind, which is a sketch of what's happening when our solar wind interacts with the local ISM. So what happens is that we have a charged proton, we have a proton that interacts and collides with a neutral hydrogen in the ISM. And due to this, we have these highly energized hot neutrals that are forming. And these produce an excess absorption component that we already heard about in the plenary today, and that can be seen in the Lyman alpha line, so in the ultraviolet. So this is the prolific technique for detecting winds in cool stars. But I want to talk about another process, which is also a charge exchange process. But in this case, we're talking about the heavier ions in the solar stellar wind. And in this case, it could be carbon or oxygen, for example. And when heavier ions meet neutral hydrogen, then the mechanism is slightly different. And I'm going to attempt to show this in this very, very badly drawn sketch. So what we have here is now, instead of a proton, we think about a heavier ion. So that collides with the neutral hydrogen. So in this collision process, what happens is that this heavier ion in the solar wind or the stellar wind traps an excited electron. And when this excited electron drops down to a lower energy state, then it emits an X-ray or EUV emission. Now, EUV, we cannot really observe from where we are standing now, but X-rays we can. And there have been multiple attempts at detecting these phenomena in cool stars, starting from the early 2000s. And until recently, we only had some upper limits. But this year, we had three direct detections of X-ray related charge exchange, which was a study led by Kristina Kislyakova. What you see here in this figure is the mass loss rate of the stellar wind, and on the y-axis, and on the x-axis, you see the X-ray flux. And the blue data points are measurements done in the X-rays using archival XMM Newton data. And the clear detections were made for 61.6, 70 off, and also for Epsilon Eridani. Whereas for Proxen and for Alpha Centauri, only upper limits could be detected. And in addition to these charge exchange in X-rays, what Christina has also plotted here are these existing power law fit to the Lyman alpha measurements, and also the black data points here represent the Lyman alpha observations for these same stars. So one thing that you could see here is that there is, of course, depending on which technique you use, the mass loss rates do differ. Of course, there are different assumptions that goes into these measurements, but the picture looks a bit bare. So this is not just the only method that has been applied to detect mass loss in cool stars. And we also heard about radio today. So I'm just going to show a summary plot. This is by Alini Pidotto, and this is a summary plot that summarizes some of the most successful techniques that have been applied to detect mass loss rate in cool stars. And the different colors here represent different techniques, and the orange one represents the Lyman alpha astrospheres method. So you can apply a parallel fit to these kind of plots, and actually you can get some information about what kind of mass loss rates we expect for stars with different X-ray activity level, for example. So this is where observations are at the moment. Of course, it doesn't include the new radio measurements that we saw today. So stay tuned. So there is more to come, of course. So then you might be asking the question, what about models? So where are stellar wind models at? So when we talk about models, then we, of course, go back to the sun, because the sun is our ideal test case, and we can actually do in situ measurements there. So from the sun, we know that the solar wind is launched around corona, and then this is where the excess heating of the corona and the wind acceleration is driven. But we still have, despite our wonderful new instruments such as Parker and also Solar Orbiter, we still have some open questions about how is the corona heated and what is the exact mechanism that's driving this heating and wind acceleration. So at the moment, our best bet is on Alphen waves, because it has been shown that Alphen waves are ubiquitous in our upper atmospheres of our sun. But nonetheless, we still don't have quite figured it out how this magnetic reconnection and Alphen waves actually interact and drive coronal heating. But the Alphen wave had been a prime driver of these solar wind models, and they have been benchmarked against in situ observations of the sun. And now, increasingly, we are also testing them out and actually using them for stellar wind models and stellar wind modeling. So when we do that, we do have to keep it in mind that although the physics is based on our sun, we can still play around with some input parameters to adapt our models to stellar conditions. And I just want to mention two interesting parameters that we have actually observations for. One would be the photospheric magnetic field geometry, and the other one will be the Alphen wave energy density. So the magnetic field geometry, of course, is a bit obvious because we did talk about it today in the previous sessions or in the plenary today. But I also want to emphasize on the fact that from observations, we can also provide a good estimate on what kind of Alphen wave energy densities are available in these kind of objects. So let me first begin by talking a bit about the photospheric magnetic field. So there is a parallel session going on magnetic fields on the other side of this room, but I just want to briefly mention where we are at when it comes to magnetic fields. So when it comes to magnetic fields, as Ansgar Reiners talked about today, we have the Zeeman effect, and when we see a Zeeman component in a spectral line, we know that it undergoes polarization states. And these polarization states depend on the orientation of your magnetic field. And what you see here in this cartoon is that if you have a magnetic field that is aligned along the line of sight, then we do expect to see circular polarization. And if you have access to a spectropolarimeter, you can actually get a wonderful, nice spectra, which will show you the Stokes V signature of this line. Now, this signature here tells us that there is a magnetic field present on the star, and we can infer what kind of field strengths this particular star might have. And we know that the star rotates, so we can actually take a series of these spectra over one rotational cycle of the star, and many people have done that. And once you have this stack of full rotational cycle of the star, you can actually run it through an inversion code to reconstruct the 2D surface map of the star's magnetic geometry from these Stokes V or circularly polarized spectra. And this is what Zeeman Doppler imaging essentially in a very, very basic, broad level is doing, right? We have Stefano who gave a talk yesterday about how magnetic fields geometries look like in stars. So you might have seen this image already. And what you see here again, just to remind you, we're looking at a flattened polar projection of the star, and where we're looking straight down along the pole. And the different circles here represent the latitudinal changes, and the solid line here represents the equator. And the red and blue basically means the magnetic field orientation, whether it's towards you or moving away from you. So this technique has been applied in the last few decades on a wide range of stars. And here, this is just an example. I've tried to provide a comprehensive list of all the work that has been done, but of course I failed because I cannot, this will be just a block of text if I just include everyone, but I still I see you get a representation of the fact that there is quite a lot of work that has been done already. And we have now snapshots of a wide range of stars. And this is just an example of PROXen done by Klein et al. From 2021. Now, in addition to the snapshots, we can also do long-term monitoring of these magnetic fields. And what we have here is just an example of how the field evolves, in this case for 61 Sig, where we start off at the very top left with a positive magnetic field that over multiple epochs then evolved to a more negative field. And then if we keep following this star, we have noticed that it actually also flips back to its red positive polarity field also. So these kind of studies have been now done for quite a wide range of stars, both exoplanet host and planets without known exoplanets. And for M stars, Stefano gave a wonderful talk today describing where we are at the moment. So this is just a bit of a overview for people who like stellar magnetic fields. But if you only care about exoplanets or for stellar winds, then the key takeaway that you should take from here is that we have Zeeman Doppler maps for a wide range of stellar properties. And these provide an important input parameter for these kind of wind models. Now, I mentioned there is also another factor that we can take into account in terms of the alpha wave energy density. So how much non-thermal heating is available for heating the corona and for launching the wind. So let me go back to this cartoon again of our very simplistic model of a star, where again, we have to go back to the sun for this. So solar physicists have long known that when you actually look at the different layers of a stellar atmosphere, and if you look, in this particular case, I'm pointing directly to the transition region, when we look at spectral lines that form at such high temperatures, this is around 60 to 80,000 Kelvin to 1,000,000 degree Kelvin, for example, then in addition to the expected Doppler broadening that you expect for these lines, and the instrumental broadening, they know that for a while now that you also see non-thermal broadening. And this is something that has been also seen in spectra taken by early observations from Hubble, for example, in the 90s. So now if you believe that these non-thermal processes or these magnetic processes that are causing this excess broadening is due to alpha wave dissipation, then you can say, okay, if I see this non-thermal broadening in stars, there is way for me to constrain what kind of alpha wave energy densities I might expect there. So this is what we did. We went back and looked at the Hubble archive, and we found around 50 plus sunlight stars. And what we see here is the non-thermal broadening measured for these particular sunlight stars using the silicon line, which forms in the transition region. And what we see here is the velocity versus the rotation period. And the different colors here represent stars for which we know calcium activity from ground-based observations. And as you can see, the sun here, which is a black star, is a sun as a star measurement taken from full disk iris observations. And as you can see that there is a tendency that most likely there is a trend where the non-thermal velocity decreases as we go for longer rotation periods, so slowly rotating stars. But again, this is again based on archival data, so there is a bit of gaps here. So I'm not going to claim that there is a trend, but I'm going to claim that there is a tendency. So, but what I wanted to point out here is that if you have these kind of measurements, and if you know what the density of your atmosphere is, you can actually provide an additional input constraint to your wind models. So this is what I wanted to say here, that when it comes to wind modeling, we have a few different ways how we can scale these models to stars and using actual stellar observations. So I want to come now to the X-ray and high energy side of things. So when it comes to high energy radiation, I'm talking primarily about X-rays and extreme ultraviolet. So for those of you who are not stellar physicists and still might be thinking, why do we care about it in terms of exoplanets? I just wanted to show this very nice sketch from Wordsworth and Freiberg, where this is a sketch of a representative rocky exoplanet. And what you see here are the different atmospheric layers. And at the right-hand side of this plot, you see the incoming radiation from the star, from X-ray, XUV to UV to visible and to infrared. And I want you to pay attention to this curve over here. That's the temperature profile, the black solid line. And the temperature profile, if you look at the top part of the atmosphere, it is really strongly dependent on the incoming radiation in the high energy for the star. because this is the part of the atmosphere where the X-rays and UV radiation gets absorbed, and it can heat the atmosphere. And at the same time, this excess heating also is, in some cases, responsible for expansion of the atmosphere, which could lead to atmospheric loss. In addition, as we also recently saw from JWST observations, that there is signatures of photochemistry that is happening in this case. It's because of the incoming radiation for the star. So that means that if we have a grasp on understanding how the XUV radiation of a star changes with stellar properties, we might be able to say something about atmospheric photochemistry and ionization and escape in these planets. So how does the XUV spectrum look like for sun-like stars? And here I'm showing an example of the solar XUV spectrum taken from Linsky et al. 2014. I see Jeff Linsky is in the audience. So this is how the solar XUV spectrum looks like. Now, if you want to do the same exercise and try to observe this in other stars, as we all know, because we're in cool stars, we cannot really do this for a wide range of stars, primarily because of neutral hydrogen that absorbs in these wavelengths. So what can we do? Well, there was a mission, as we know, in the past, the EUV, which did observe in this particular wavelength range for a limited number of nearby stars. And there are some observations of cool stars available. There is this nice catalog of stars from Craig 1997. Now, the problem is that these are well-known active stars, and these are not necessarily a representation of exoplanet host stars. So you might be thinking, then how can we improve on this? So this brings me to one of the few last slides. So what we have here is that there are multiple different ways and the EUV has been reconstructed. And I try to include a few more different citations here. But what I want to show here is this one plot from Claire et al. 2012. So in this particular case, the solar spectrum was taken as a template with empirical scaling laws. And what we see here is the modern sun, which is shown in green. And the method that Claire applied, their technique to determine what the XUV would be for an early young sun. And for comparison, the EK draw spectra in the X-rays and UV is also shown here. So in addition to this, there are different other techniques. For example, there has been methods used just X-rays or the far UV side of things. There has been also physical models of the stellar atmosphere that has been used to reconstruct this part of the spectrum. But of course, depending on which method you use, which method you like, your favorite method, there might be some biases based on the exact technique you use. And this is where I want to show one example of why this particular wavelength range really matters. Is I wanted to show some results done by Gwenal van Luberen, a PhD student in our group, who studied the impact of XUV on an atmosphere, in a 1D atmosphere comprising of carbon dioxide and nitrogen. So this is for the TRAPPIST-1 rocky planets. And one of the things that one of the key results was that when you actually do the simulations to understand how long does an atmosphere last due to the high energy radiation of the star, then you find that while the planets themselves are in the habitable zone, the atmospheric retention distance is much, much further out. So the planets over there in the habitable zone do not really have a chance of surviving, not planets, the planetary atmosphere. And this is something that is quite interesting because the atmospheric retention distance and the habitable zone do not really overlap in here. But for our XUV spectra itself, how you generate this XUV spectra matters, because this is, again, another simulation done for this nitrogen and oxygen, carbon dioxide dominated atmosphere, where the input spectrum is different. One was the case for the solar spectrum, which has been scaled to the TRAPPIST X-ray flux. And the other one is a TRAPPIST-1 spectrum taken from the mega muscle survey. And depending on which spectra you use, the thermal profile also changes, and that has an impact on the chemistry. So this brings me to the last bit, just to summarize. So for exoplanets, stellar winds are essentially very important when it comes to the non-thermal loss processes. And the XUV spectra, of course, is also impacting photochemistry and ionization in these cases. So where are we at in terms of stellar winds? We are now able to detect stellar winds with wide range of observation techniques, but we still have limited number of stars for which we can carry out these different techniques. Based on the sun, we have tried to understand now what is the exact physical mechanism that's driving these winds. And I think we are getting closer and closer to the answer, but still not quite there yet. But we do have stellar observations that we can use if we want to take the solar model and then adapt it to stellar cases. Now, when it comes to XUV, of course, because it gets absorbed, we need to come up with some creative ideas on how to reconstruct it. And I think there is still quite a lot to be done to understand how can we combine all of these processes to come with a coherent answer for the XUV. So yeah, that's it for now. So thanks very much. Thank you very much. Yeah. Yeah, that's a good question. I do not know. I think you have to really think about of course, depending on how energetic the CME particles are, of course, and what is the CME made out of, what is the chemical composition under quotation mark, right? So yeah, it's difficult to say. Yeah. Oh, sorry. Yeah, I think the question is about for the XUV reconstruction, what about flaring and not on transient parts? I think there was a talk today and the last talk in the plenary session where there was a talk about flaring, right? And how it impacts in the flaring in the UV and in the XUV in general. I think for that, we would need to know what the flaring rates are, of course, and we need to have observations in those wavelength ranges. So, I mean, in principle, if you have those rates, you can construct a spectrum, but then it's very heavily dependent again on your assumptions there also, right? So, yeah. Yeah, so I'll just repeat your question. Thank you for this very great question, actually. So, so the question is about the atmospheric retention distance and the habitable zone. At what masses, stellar masses, would you see that overlap, right? So, so we thought about this when we came up with this plot to how to extend it into higher masses. Of course, it will depend on the kind of planet that you're talking about. And if you just assume that it's a TRAPPIST mass planet, but with around different other stars, we actually did do this study also. So it's a work in progress. So keep an eye out for the paper. But the point here is that we need to go to higher masses. We need to go to at least uppercase or G stars to be able to see that. But again, keep it in mind that this is just for CO2 and N2 composition. And we also do not take into account for bigger masses, right? But if the planet itself is higher masses, assuming TRAPPIST-1 conditions and changing the star, yes, we need to go to higher masses in that case, yeah.
Very good talk.
Thank you.
I just want to point out that it's really important to go beyond the XUV flux to speculate. If we go back to slide 38, I think really illustrates the point very well. Namely, as you go through the more active regions of the sun, it's the X-rays that really dominate the screen multiplier. And really, the X-rays first penetrate deeper the atmosphere, photo absorb higher up in the atmosphere, and the relative importance of screen ultraviolet and the X-ray really needs to be
Yeah, I absolutely agree with that. Yeah, thanks for pointing it out. Because I think we are very good, I think, at the moment to understand how the total flux in different wavelengths scale with different activity indices and things like that. But when it comes to the spectrum itself, how is the spectrum dependent on stellar properties, activity, etc.? It is not known, and it depends which assumptions you make, how you're reconstructing this. And theoretical work needs to be done on that, of course. I do want to highlight one thing, that when we are looking into this TRAPPIST-1 case with the different XUV spectrum, one of the reasons that we actually get this different temperature profile that I show here is because we are looking at a carbon dioxide dominated atmosphere, and where the two spectra, the XUV spectra, differ is in the UV wavelength range, right? And this is where we have the absorption cross sections of CO2, and that really, really changes things depending on the spectra. So we should be really careful when we're doing this kind of atmospheric photochemistry and thermal models in this case, yeah. Yeah, thank you.
Test, test. Can everyone hear me? What's the audio? No worries. Okay, cool.